So we're going to start talking about the quantum mechanical model, and to do so, we're going to begin just with a quick discussion about the two people really involved in it, Werner Heisenberg and Erwin Schrodinger. So Werner Heisenberg, he attempted to find the location of where the electron is. So much like how we had mentioned previously that the Bohr model made the assumption that the electron revolved around the nucleus, the quantum mechanical model assumes that there is no actual constant path. So Heisenberg devised an experiment to try to figure out exactly where to find the electron. To do so, he used a particle that's very, very close in size to the electron, known as a photon. A photon is essentially a particle of light or energy. When he tried to hit an electron with this photon, he found that the velocity of the electron changed. So every time he tried to hit the electron with this photon, the electron would either slow down or speed up. At this point, he concluded that the exact position, so where the electron is, and its velocity, how fast it's moving, cannot be known at the same time. This resulted in the formation that's widely known as the Heisenberg uncertainty principle. Essentially, that an object's exact position and exact velocity cannot be known at the same time. You have to choose either or to study. So then we move on to Erwin Schrodinger. Schrodinger, as we mentioned previously, constructed this math equation known as Schrodinger's equation that can help you find the energy and the location of an electron. So using this information, it's possible to actually identify using with closest probability where the electron might be. So this equation right here, also rewritten in this form, where the Hamiltonian operator times your wave function is equal to the energy of the electron times its wave function. So our eigenfunctions and our eigenvalues here, just a little high-level math there, going over how to solve this equation, that if you can, using this, you can figure out the energy of the electron and also its location here. So solving it provides the probability of where it is. Now it's not going to be 100% certain, but it's probability. So the areas with the highest probability are referred to as the atomic orbitals. So by solving Schrodinger's equation, you essentially have an idea of where the electrons are more likely to be. And these areas with the highest probability we call the atomic orbitals. So as I mentioned before, the atomic orbitals are the area with the highest electron probability, basically where the electrons are more likely to be. So the energy levels in the quantum mechanical model, we label them by what's called the principal quantum numbers. So these tell you what the different energy levels are. And again, this is done by solving the Schrodinger equation. Now at each energy level, there may actually be several orbitals that have different shapes and energies within them. You could think of these energy levels as like the floors of a building. So in the principal quantum number, denoted by the letter n, this actually describes the size of the orbital. We number them 1, 2, 3, and so on. And again, that just tells you how large that orbital is. How large is the energy or the probability of finding an electron in there. So as the principal quantum number or the energy levels increase, the size of the orbital increases as well. Next is what's called the angular quantum number. This describes the shape of the orbital. And it can either take on what's called an S, P, D, or F shape orbital. Again, these are calculated and found by solving Schrodinger's equation, and these just help to better specify where to find the electron. So all of these just add more exact coordinates exactly on where the electron might be, where it's most likely to appear to. So the principal quantum number tells you the size of it, while the angular quantum number gives you the shape of the orbital. Moving on, we have what's called the magnetic quantum number. This describes its orientation in space. Because all of this is happening in 3D, we are free to rotate. Right? So on a 3D plane, it's actually possible. So if we have our x and y, we also add on what's called the z plane. And in this plane, our orbitals are free to rotate. 3 dimensions. It's a real life. So the magnetic quantum number will tell you about the orientation, basically what the shape is going to be as you rotate around it. And then lastly, the magnetic quantum number goes over the spin of the electron. So it's either going to be clockwise or counterclockwise. Now all of this is just to give as much information about where the electron is in the atom, how it's moving. That's the entire goal of quantum mechanics. Study the electron. How does it move? How does it behave? And all these different numbers give us an idea of how to better study and to give us as much information about the electron as we possibly can. So it's a lot of information. To condense it down, we have what's called the electron configuration. The electron configuration describes the arrangements of the electrons around the nucleus. So it kind of takes into account all of the different numbers that we just went over, where they're found in the different orbitals around the nucleus. It's essentially like the coordinate point to the electron. So to determine the electron configuration of an element, you're going to have to follow three rules: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Now, following these rules to build the electron configuration gives you the best idea of where the electrons in an atom are more likely to be found. Okay, so starting off with the first rule, the Aufbau principle assumes that electrons will always occupy the lowest energy orbitals first. So electrons will always go ahead, fill in the orbitals that are closest to the nucleus, the ones lowest in energy first before actually moving on to areas of higher energy. The second rule is the Pauli exclusion principle, saying that the orbitals can actually only hold two electrons at the most, and the two electrons have to be spinning in opposite directions. So meaning one electron has to go clockwise while the other one is moving counterclockwise. So an orbital can only hold two electrons and they both have to have opposite spins to each other. And the last rule here, Hund's rule, well, this rule assumes that the electrons will occupy the empty orbitals before doubly occupying the ones that are already filled. Meaning electrons would prefer to have the same spin and be by themselves before having to occupy an already occupied orbital. We'll see exactly what all these rules mean and how to put this into practice. So here's what's called an energy level diagram. It takes into account the different principal quantum numbers. You see the 1, 2, 3, 4, and so on. The angular quantum numbers, hence the shape, S, P, D, F. It includes also the orientation, where the p orbital will have 3 different orientations based on how it's going to rotate. The d orbital has 5 different, and the f has 7 different. Just kind of going back here, you can see how these p orbitals are different. It's all depending on how it's going to be rotated around the origin, assuming a 3D plane. So if we were to go ahead and say we want to know the electron configuration for hydrogen, well, we're going to use this diagram here to try to figure out where is this electron for hydrogen. So we're going to be using arrows here, more specifically a half arrow, to label exactly where the electrons are. Okay, so following the first rule, Aufbau principle, electrons occupy the lowest energy orbitals first. So that means at the lowest possible energy, that's where electrons are going to start occupying. Now hydrogen's only got 1 electron. So for hydrogen, its 1 electron has to follow the first rule. It's going to be right down here, the lowest possible energy at the 1s orbital. We're going to show a half arrow there. That means my 1 electron is at the 1s orbital. The electron configuration for hydrogen is then written as where the electron is. It's in the 1s orbital. And right up here, as like an exponent for the s, we're going to identify how many electrons are there. Well, in the 1s orbital, there's only 1 electron. So we say that the electron configuration for hydrogen is 1s1. This tells me the electron exactly where it is. It's at the 1s orbital, and I've only got 1 electron. Okay, let's move on to helium. Helium's got 2 electrons. Okay, so we already know that 1 electron fills up this orbital. Now we also know by the Pauli exclusion principle that the atomic orbitals can hold 2 electrons. So if we're going back here, we have a second electron to put. This orbital can hold 2 electrons. We have to still follow the Aufbau principle that the lower energy levels are filled up first. So the fact that this one can hold 2 electrons means another electron still fits at the 1s. But the second part of the Pauli exclusion principle states they must have opposite spins. So that means that we have to show that there's a second electron in here and it's spinning in the opposite direction as the other electron. Well, to show that they're going to be opposite to each other, I have already an up arrow. I'm just going to go ahead and draw a down arrow. So this right here tells me that I have got 2 electrons in the 1s orbital, and they're both spinning in opposite directions. So the electron configuration for hydrogen is then shown as 1s, because that's where my electrons are, and now I've got 2 of them. So both of the helium electrons are found here in the 1s orbital. Continue on to lithium. Okay. So lithium's got 3 electrons. So now for lithium, okay, we want to go ahead, we already got 2 electrons here. So instead of putting a third electron here, we can't, because every orbital, every line here can only hold 2. So that means we say this orbital here is full. So now we move on to the next one. Again, still following the Aufbau principle, we occupy the lowest energy ones first. Because the lowest possible is full, we're going to go to the second lowest, right here, the 2s. Now I've got one more electron to take into account of. So now I've got my 1, 2, 3 electrons for lithium. So the electron configuration for lithium takes into account where all of the electrons are found. So in the 1s orbital, I have 2 electrons. In the 2s orbital, I have 1 electron. This right here tells me that 1s I have 2 electrons, and in the 2s I've got 1 electron. And then we continue on to beryllium. Okay, beryllium's got 4 electrons. Okay, so I've already got 1, 2, 3 electrons to account for. I have this 4th electron. Now I have this 2p orbital here. But before I can start getting to that one, we have to remember the Pauli exclusion principle, that each one of these orbitals can hold 2 electrons. So I need to fill up this one before I can move to 2p, because 2p is at a higher energy. So just like how we did before with helium, I'm going to show that the second electron and it has an opposite spin to fill up this orbital. So now beryllium's electron configuration, 1s2, 2s2, tells me that I've got 2 electrons at the 1s orbital and 2 electrons at the 2s orbital. So now let's go to boron with its 5 electrons. Okay, we've already got 4 electrons accounted for here. So now when I have to go place my 5th electron, okay, this orbital's full, this one's full. The only one left now is the 2p orbital. Now I can go ahead and start filling this one. So now for boron, again I have to show where all of the electrons are. That is what we care about, their locations. So in 1s I've got 2 electrons. In 2s I've got 2 electrons. And now in 2p I've got 1 electron. So now we move on to carbon with the 6 electrons. So we already got 5 here. And now it's time to put the 6th electron. So let's go ahead and add our 6th electron. Doing so actually breaks the 3rd rule. So if we go back and take a look at this 3rd rule, electrons occupy empty orbitals before having opposite spins. So what that means to say is that this electron right here, well, while it could go ahead and pair up with this other electron in that orbital, there's 2 other ones that are available. They're all at the same energy, so they all have the equal opportunity to get filled by that 1 electron. So that electron is actually going to go ahead and end up being by itself first before pairing up. It's much like if you have 2 kids who don't like each other, They much rather sit apart from each other before being next to each other. So this third rule, Hund's rule, tells us that we must fill each orbital with at least one electron before pairing them up. So for carbon, we have our 1s2, 2s2, and now in the 2p, okay, all of these three orbitals belong to 2p. This is your 2px, your 2py, and your 2pz. These are all formed by the different orientations of the 2p orbital in which it gets rotated in space. So in the 2p orbital, even though there's 1 in x, 1 in y, all of these belong to 2p, so we'll say there are 2 electrons in the 2p orbital. So carbon electrons are found at 1s, 2s, and 2p. Okay, next up, nitrogen. So that's got our 7 electrons. Once again, we have 6 of them. We have to put the 7th one somewhere. Now if we take a look here, much like how we did it in the first, double pair this up in the first example with carbon, we're not going to do that yet either. With nitrogen, we still have this one opening here. So until everything is filled up with at least one electron, we're going to keep putting it in the empty spots. And so nitrogen's got a configuration of 1s2, 2s2, 2p, and again, all three of these are still in the 2p orbital. So we're going to say it's a 2p3. And our last one that we're going to do, oxygen, with our 8th electron. Okay, we've got 7 here. Now, oxygen with the 8th electron, we don't go to this 3s just yet, because we know that every single one of these orbitals can still hold 2 electrons. But now there's no empty electron. So there's no way this electron can go ahead and be in an orbital by itself. Now it has to be paired up. So we'll say that the electron for configuration for oxygen is 1s2, 2s2, 2p4, because there's 4 electrons here in the 2p orbital. Here we got 1, 2, 3, and 4. And again, we'll continue on pairing these up. It's not until each one of these orbitals has 2 electrons can we start to move up to 3s and so forth. So these electron configurations tell you exactly where to find the electrons. And it's all because of the Schrodinger equation figuring out the highest probability of where to find electrons based on their energy levels.